Yes, the statement is true. The National Electrical Code states in Article 312.5d that a common neutral is a single neutral conductor used as a neutral for more than one set of feeder conductors. It shall have current carrying capacity equal to the sum of the neutral conductor capacities of the individual neutral conductors if an individual neutral conductor were used with each feeder set. This requirement is only applicable to feeders. It specifically states that a common neutral may be used only with feeders. Therefore, it is not permissible to use a common neutral with branch circuits. The neutral of a multi-wire branch circuit is not considered a common neutral because it is only used for a single circuit, even if the circuit consists of multiple wires. In a three-phase system, a 42-circuit panel with 42 single breakers for branch circuits would typically require 42 neutral conductors. This is because the NEC requires an individual neutral conductor for each branch circuit. While it is common practice to use a common neutral for the three phases in a three-phase system, this is only permissible for feeders, not branch circuits. In this case, you would need three different common neutrals, one for each phase A, B, C. You should never have two branch circuits from the same phase on a common neutral. The statement that a common neutral may not be used with branch circuits is true. In a three-phase system with multiple branch circuits, each branch circuit must have its own individual neutral conductor, unless it is a multi-wire branch circuit. Let's delve into the specifics of neutral conductors in electrical systems, focusing on the National Electrical Code or NEC requirements. We'll examine the differences between feeders and branch circuits and clarify the proper application of common neutrals. The NEC is a comprehensive set of standards that govern electrical installations in the United States. It's designed to ensure safety and prevent electrical hazards. Understanding the NEC is crucial for electricians, engineers, and anyone working with electrical systems. Article 312.5d specifically addresses the use of common neutrals. A common neutral, as the name suggests, is a single neutral conductor shared by multiple circuits. However, the NEC strictly limits the use of common neutrals to feeder circuits only. Feeders are the conductors that carry electricity from the service equipment, such as the main panel, to subpanels or other distribution points. Branch circuits, on the other hand, are the circuits that extend from the final overcurrent device, like a circuit breaker, to the electrical loads such as lights, outlets, and appliances. The NEC prohibits the use of common neutrals for branch circuits. This means that each branch circuit must have its own dedicated neutral conductor. The reason for this restriction is to prevent overloading the neutral conductor and potential safety hazards. When multiple branch circuits share a common neutral, the neutral conductor can become overloaded if the current flow from the different circuits is not balanced. This overload can cause the neutral conductor to overheat, potentially leading to a fire. In a three-phase system, which is commonly used in commercial and industrial settings, the NEC requirements for neutral conductors are particularly important. A three-phase system consists of three alternating current conductors, each carrying a voltage that is 120 degrees out of phase with the others. In a three-phase, four-wire system, a neutral conductor is also provided. The neutral conductor provides a return path for unbalanced currents. Unbalanced currents occur when the loads in the three phases are not equal. In a three-phase system with multiple branch circuits, each branch circuit must have its own dedicated neutral conductor. This is because the current flow in each phase can vary independently. If branch circuits from different phases were to share a common neutral, the neutral conductor could become overloaded if the current flow from one phase is significantly higher than the others. However, there is an exception to the rule that each branch circuit must have its own dedicated neutral conductor. This exception applies to multi-wire branch circuits. A multi-wire branch circuit is a circuit that consists of two or more ungrounded conductors and a neutral conductor with a voltage between the ungrounded conductors. Multi-wire branch circuits are commonly used to provide both 120 volts and 240 volts power. In a multi-wire branch circuit, the neutral conductor is only shared by the ungrounded conductors of that specific circuit. The neutral conductor is not shared with any other circuits. This arrangement is permitted because the current flow in the neutral conductor of a multi-wire branch circuit is typically lower than the current flow in the ungrounded conductors. This is because the currents in the ungrounded conductors tend to cancel each other out in the neutral conductor. In a 42 circuit panel with 42 single breakers for branch circuits, you would generally need 42 neutral conductors. Each branch circuit requires its own dedicated neutral conductor. While using a common neutral for the three phases in a three-phase system might seem efficient, it's only permissible for feeders, not branch circuits. For branch circuits, each circuit needs its own neutral. If you're dealing with a three-phase system, you'd need three different common neutrals, one for each phase A, B, and C. It's crucial to never connect two branch circuits from the same phase to a common neutral. That's a recipe for potential problems and code violations. In summary, the NEC strictly regulates the use of common neutrals, limiting them to feeder circuits only. Branch circuits generally require individual neutral conductors, with the exception of multi-wire branch circuits where a single neutral serves multiple ungrounded conductors within that specific circuit. Always consult the NEC and a qualified electrician to ensure your electrical installations comply with all applicable codes and regulations. Doing so helps to ensure the safety and reliability of your electrical system. It's also worth noting that local electrical codes may have additional requirements or restrictions regarding the use of neutral conductors. Therefore, it's always a good idea to check with your local authorities to ensure that your electrical installations comply with all applicable codes and regulations. When working with electrical systems, safety should always be your top priority. Always disconnect power before working on any electrical components. Use appropriate safety equipment, such as insulated gloves and safety glasses. And if you are not comfortable working with electricity, always call a qualified electrician. Understanding neutral conductors is essential for safe and compliant electrical installations. Firstly, it's the code. Adhering to the NEC is not optional, it is the law in many jurisdictions. Failure to comply with electrical codes can result in fines, penalties, and even legal action. Secondly, safety. Electrical systems can be dangerous. Improper wiring can lead to electrical shocks, fires, and other hazards. Following the NEC helps to minimize these risks and protect people and property. And thirdly, performance. Properly wired electrical systems perform better and last longer. Compliance with the NEC ensures that electrical systems are installed correctly and that they meet the required standards for safety and performance. When installing or modifying electrical systems, it is essential to consult the latest edition of the NEC and to follow all applicable requirements. It is also recommended to consult with a qualified electrician to ensure that the work is done safely and correctly. Here are some additional points to consider regarding neutral conductors in electrical systems. The size of the neutral conductor is determined by the size of the ungrounded conductors in the circuit. The NEC provides tables that specify the minimum size of the neutral conductor for different size ungrounded conductors. The neutral conductor must be insulated in certain situations. For example, the neutral conductor must be insulated if it is run in the same raceway as ungrounded conductors that are operating at a voltage of more than 300 volts to ground. The neutral conductor must be grounded at the service entrance. This grounding provides a path for fault current to flow back to the source, which helps to protect people and property from electrical shock. The neutral conductor must be continuous and unbroken. It cannot be spliced or interrupted between the service entrance and the branch circuits. The neutral conductor must be identified by a white or grey color. This color coding helps to distinguish the neutral conductor from the ungrounded conductors, which are typically black or red. It is important to note that the information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician before working on any electrical systems. The NEC is updated every 3 years, so it is important to stay up to date with the latest edition. The NEC is available for purchase from the National Fire Protection Association. Many online resources are available to help you understand the NEC. However, It is important to use these resources with caution and to verify the information with a qualified electrician. The NEC is a complex document, and it can be difficult to understand all of the requirements. If you have any questions about the NEC, it is always best to consult with a qualified electrician. Understanding the NEC is essential for anyone working with electrical systems. By following the NEC, you can help to ensure the safety and reliability of electrical installations. Common neutrals can create harmonic currents, which can overload the neutral conductor and cause overheating. Harmonic currents are multiples of the fundamental frequency of the AC power system, which is typically 60 Hz. These currents can be generated by nonlinear loads such as electronic devices and some types of lighting. To mitigate the effects of harmonic currents, it is important to use oversized neutral conductors and to install harmonic filters. In some cases, it may be necessary to use a separate neutral conductor for each phase of a three-phase system. This is especially important in systems with a high percentage of nonlinear loads. Neutral conductors must be properly terminated. Loose or corroded connections can cause overheating and voltage drops. Terminations must be made with approved connectors and must be torqued to the manufacturer's specifications. Neutral conductors must be protected from physical damage. They should be run in conduit or other protective raceways. Where exposed, they should be protected from impact and abrasion. When working with neutral conductors, it is important to use appropriate safety precautions. Always disconnect power before working on any electrical components. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electricity, call a qualified electrician. The NEC provides specific requirements for the grounding and bonding of electrical systems. Grounding is the connection of the electrical system to the earth. Bonding is the connection of different metal parts of the electrical system together. Grounding and bonding are essential for safety and help to prevent electrical shock. The grounding electrode conductor connects the grounding electrode to the electrical system. The grounding electrode is typically a ground rod, a metal water pipe, or a concrete encased electrode. The equipment grounding conductor connects the metal parts of the electrical system to the grounding electrode conductor. This conductor provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker and de-energize the circuit. Bonding jumpers are used to connect different metal parts of the electrical system together. These jumpers ensure that all metal parts are at the same electrical potential, which helps to prevent electrical shock. The NEC provides specific requirements for the size and installation of grounding and bonding conductors and equipment. It is important to follow these requirements carefully to ensure the safety and reliability of the electrical system. In addition to the NEC, there are other standards and regulations that may apply to electrical installations. These include local building codes, utility company requirements, and industry standards. It is important to be aware of all applicable requirements and to comply with them. Working with electrical systems can be dangerous, and it is important to take appropriate safety precautions. Always disconnect power before working on any electrical components. Use insulated tools and wear appropriate personal protective equipment. If you are not comfortable working with electricity, call a qualified electrician. Electrical safety is everyone's responsibility. By following the NEC and taking appropriate safety precautions, we can help to prevent electrical accidents and injuries. The proper installation and maintenance of neutral conductors are essential for the safe and reliable operation of electrical systems. By understanding the requirements of the NEC and taking appropriate safety precautions, we can help to prevent electrical hazards and protect people and property.